Okay, we'll be looking at the problem in the first buffer section in your work packet. I recreated the problem. This is problem number 2. Okay, so we're going to calculate the pH when 20 milliliters of a 0.1 molar nitric acid solution have been added to 25 milliliters of a 0.1 molar potassium hydroxide solution. Hopefully the first thing you recognize when you look at this is that this is an acid, nitric acid, and that this is a base. Okay, so then you should think to yourself, is this a strong acid or a weak acid? Is it a strong base or a weak base? From the 7 that you have to memorize, this is indeed a strong acid. And this potassium hydroxide, remember hydroxides of the alkali metals, which are group 1, and the heavier group 2, which is calcium, barium, and strontium, are strong. So this is a strong base. Okay. So because we're not dealing with anything weak, we're not likely to have an equilibrium. So let's see what happens when we mix these two. And you do need to remember that an acid plus a base, when they react, form a salt and water. So if we do the chemical equation, we have the acid in solution, and we have the base in solution. Any stoichiometry we're going to assume goes to completion. Okay, so there is no equilibrium. And remember, acid and base, it's really just for the most part, a double replacement. I'm so not used to my pen. And water. I don't know what that mark was. Okay, now we should be able to calculate the moles of each, right? And I'm going to do what's called a before, change, and after table. And this is just a way of keeping track of the moles. All right, it's a before, change, and after, or a BCA table. And this is in moles, which is different from an ice table, which you would use with an equilibrium, and that has to be concentration. So I've got to calculate the moles of each. Hopefully you remember. I'm going to change it into red. So moles of acid. I have a volume. I'm going to change that 20 milliliters to a liters times the concentration. Bless you. Bless you again.
Sorry.
Okay, so that's moles of of nitric. And then I have 25 milliliters. And I should put a 0. And a 0 there. 0 there. Times your concentration for the base. This should be labeled moles of base. Over 1 liter, that is the concentration. This is moles. I do get a little sloppy. 0.0250 moles of the KOH. So filling this into the BCA table, and this is why using a BCA table sometimes helps you see it. So I have 0.002 moles of the nitric. I have 0.00250 moles of the potassium hydroxide. Initially, I've not made any salt, and I haven't made any water, although there will be some in the solution, because it's aqueous solution, so I have a lot of moles actually. All right. Hopefully you can see that this, the acid, is your limiting reactant. So this is as much or as many moles as can react. Because it's a 1-to-1 ratio, and I'm looking again at the balanced chemical equation, the number of moles of potassium hydroxide that are going to react are the 0.002 moles. Okay. Because again it's a 1-to-1 mole ratio, I'm going to make 0.00200 moles of the potassium nitrate, and I really don't care what the water is doing because it is an aqueous solution. After the reaction is complete, I'm not going to have any nitric acid left over. I'm going to have 0.00050 moles of potassium hydroxide remaining. I'm going to have 0.00200 moles of potassium nitrate. We are looking for the pH. What do I have in solution? I have potassium hydroxide and I have potassium nitrate. I'm going to move this up just a little bit. So what are these going to do in solution? Potassium hydroxide is soluble, right? So I'm going to have potassium ions, and we're going to have hydroxide ions. Potassium ions not going to affect the pH. This definitely will affect the pH. I have potassium nitrate. Potassium ion not going to affect the pH. Nitrate ion is an anion of a strong acid, so that's going to stay in solution. That's not going to affect the pH. But my hydroxide is. And if we remember, I'm going to go with the pOH is equal to the negative log of the concentration of the hydroxide ion. It's the concentration of the hydroxide ion. What is the concentration of the hydroxide ion in this solution? Well, it's going to be the number of moles of the hydroxide ion over the total volume. That's going to be your 20 milliliters plus your 25 milliliters. If you convert that to liters and look a little bit harder at the significant figures, it would be 0.0450 liters. So the concentration of my hydroxide ion is 0.01111. I'll add that. And that is molarity of my hydroxide. So my pOH is equal to the negative log of that. I get 1.9542. pH is equal to 14 minus the pOH, so that is equal to 12.0457. Significant figures, if we go back up to the top, see what our given significant figures were. We've got three significant figures, 3 and 3, so my answer should be to 3 significant figures. For a pH, remember it is the number of decimal places behind the pH, so my answer should be reported as 12.046. Okay, that's the end of the screencast.